Hello everyone, welcome to another video lecture of Mathematics Solution channel, and today we are going to discuss about the Cauchy integral theorem. So what is that Cauchy integral theorem? If f of z is an analytic function inside on a closed or simple closed curve C, and they are given on point if A is any point within the circle C, right? Then we need to prove f of a is equal to 1 by 2 pi I integral over c f of z divided by z minus a into dz. This is what we need to prove. And before that, before going to prove this theorem, I'll take, here it is the x-axis and the y-axis. So given that C is any closed curve, let us take C is the closed curve, okay, and within the circle A is any point, A is any point. So this is the A. I'm going to consider one more circle which is extremely inside in the given circle with the radius r. The point A is the same thing, and I'm going to mention this U1 is the another circle. And this is the region, capital R, or we can take it as a D, that is called angular region, right? Now we need to prove that f of A, the point f of A is equal to 1 by 2 pi I integral over C f of z divided by z minus a into dz. To prove this theorem, we need to recall some basics or some Cauchy's theorem. So what is that? First one, here it is, integral over c f of z dz is equal to 0. This is called Cauchy's theorem. And one more theorem we need to recall, that is called the extension of Cauchy's theorem, that is for two curves. So what is that extension of Cauchy theorem? Integral over c f of z dz is equal to integral over c1 f of z into dz. The function f of z divided by z minus a is analytic inside in the angular region within the circle C and C1. Now using that, this can be written as integral over c f of z divided by z minus a into dz, which is equal to integral c1 f of z divided by z minus a into dz. Now this is the circle with the center A and radius is r. We know the circle equation, right? So what is the circle equation? Z minus a, that is modulus of z minus a is equal to r. And then just recall the parametric equation of this equation, circle equation, z minus a is equal to r into e power I theta. Now here we need to find f of z minus a into dz. Therefore z is equal to a plus r into e power I theta. Then what about dz? Just differentiate here. You will get 0 plus r into, r is the radius, is the constant value, then e power I theta into I, theta will become d theta. Now we got all the values, substitute here. This is only for the circle C1, okay, and this will become integral over c f of z divided by z minus a into dz is equal to integral over c1 and f of, what is the z value? Here it is, a plus r into e power I theta divided by z minus a here. So z minus a is equal to r into e power I theta into dz, that is r into e power I theta into I into d theta. Now we need to find the limit of this integration. What is the limit of this? This is the circle, therefore definitely the theta is varies from 0 to 2 pi, because chart from 0 ends with 360, therefore the limit is varies from 0 to 2 pi. I can replace the directly limit here, that is 0 to 2 pi, and if any common term just cancel, so r, this value will get cancelled. Then integral 0 to 2 pi f of a plus r into e power I theta into I into d theta. We can take this I outside, that is I into integral 0 to 2 pi f of a plus r into e power I theta into d theta. Now we used one, the given statement is f of z is an analytic inside on a simple closed curve C, right? Only we have C. So we need to eliminate this C1. How to eliminate this C1? If I make this R, that is radius is 0, if I make the radius is 0, so this circle will be eliminated, correct? So just take R tends to 0, correct? The circle will be shrink and it will disappear. Then R tends to 0, substitute here, integral over C f of z divided by z minus a into dz is equal to I into 0 to 2 pi f of a, this value will become 0 into d theta. Now integrate here, f of a is a constant value, we can take it out, I into f of a integral 0 to 2 pi into d theta. If you integrate this, you will get I into f of a into theta, the limit varies from 0 to 2 pi. If you substitute 0, this term will become 0. If you substitute 2 pi, you will get 2 pi. So here, which is equal to I into f of a into 2 pi, which is integral over c f of z minus a into dz. We need to find f of a value, that is what they are given. So f of a is equal to, keep this one side or operate I into 2 pi both the sides, you will get 1 by 2 pi I integral over c f of z into dz divided by z minus a. This will give the proof of the Cauchy integral theorem. And based on this equation, we can verify one problem. So first one, let us take evaluate integral over c f of z. So this f of z, let us take e power z divided by z minus 2 into dz. So this is what we need to prove. And already we have integral over c, here also integral over c. In place of f of z, we have e power z minus a. Therefore the center of this circle is 2 here. Therefore just compare here. Solution, we know the equation, that is f of a is equal to 1 by 2 pi I integral over c f of z divided by z minus ca into dz, where a is equal to 2 here, and substitute f of 2 is equal to, correct, f of 2 is equal to 1 by 2 pi I integral over c, what is f of z, e power z divided by z minus 2 into dz. Now we need to find only this value, so bring all the terms here, and before that we need to find f of 2. We know what is f of z, f of z is equal to e power z. Therefore f of a is equal to, that is f of 2 is equal to e power 2. Now substitute in this value here, what you will get? F of 2, that is e power 2 is equal to 1 by 2 pi I integral over c e power z divided by z minus 2 into dz. We need to find only this value, bring all the terms here. So 2 pi I into e power 2 is equal to integral over c e power z divided by z minus 2 into dz. So that's it. This is the problem which is using by the Cauchy integral theorem. If you like this video, please subscribe my channel for more updates, and thanks for watching.